ठीक आहे. ऑडिओ चेक करून घे. Dr. Nishima will be talking about it. What we have in store today is, because this lecture series is for, or this particular lecture is for chemistry being organized in physics, and I think I see faculty members from all disciplines, that really makes us multidisciplinary. All my colleagues who are sitting in front of the dais, I welcome Professor Arun Grover, our ex-Vice Chancellor, Professor Navdeep Goyal, my colleagues from Chemistry Department, Dr. Rohit Sharma, the DSW women, Dr. Simrat, and all my colleagues from Chemistry and Physics. So I would now request Professor Arun Grover to briefly talk about these lecture series. Professor Grover, please. Thank you.
Good morning, all. Let me first start by apologies. The lecture was supposed to be at 11, but while sending the minute-to-minute program, I made a mistake. In the cut paste, I put it 11:30. So I'm sorry for that. So this lecture series, which is on behalf of SPSTI, Chandigarh chapter of National Academy of Sciences in India, India's North North Zone North Central Zone chapter, CRIC-C and CRIC institutions, which of course includes Punjab University, which started the whole thing as a CRIC-C long ago. So this lecture series during the years of pandemic ran in a online mode. And so in some sense, this is 20, 21, 22, 23. This is the fourth year in a row. First 3 years, we ran it in an online mode. And the Nobel Prize lecture series covers 9 lectures in all, 6 of the Nobel Prizes, 1 on the Turing Award, 1 on the Nobel Prize, and the other on the Ford Prizes. So Nobel Prizes, as you know, are announced in October, and then Nobel Prize and Turing Awards are done in March, and the World Food Prize comes in the month of May. So this year, we have covered only 3 lectures so far, namely the Nobel Prize for Medicine and Physiology, Literature, done on 20th of November in the English department. And this is the 3rd lecture, which is being hosted at the Physics department in the Punjab University. So there are 3 more lectures in the Nobel Prize series left. We had intended to complete it before December 10, but unfortunately, for a variety of reasons, it hasn't been possible. One of the main reasons is that President SPSTI wanted this year's lectures to be done in a hybrid mode. For a hybrid mode, we need audience, and things were clashing with the students' exam schedule and various other things concurrent going on in parallel in the university. So we have to do something about it next year so that we adhere to the schedule. We are lucky that this year the National Academy of Sciences of India Chandigarh chapter has received ₹5 lakh for the outreach activities to be done in partnership with SPSTI, CRIC-C, and other organizations which are a part of our conglomerate. So this ₹5 lakh has 4 verticals. One of the verticals is, of course, holding the expository lectures, and we are supposed to have minimum of 1 lecture a month. So there are other 3 verticals relate to extending the outreach of science to the rural areas. Every institution is supposed to adopt 5 villages and so on and so forth. So and then we are also supposed to engage with the summer students. Summer students do come in to work with the professors in the universities and fellows of the academy in our region. But that program also is not very well organized. It runs between individuals and an individual. So this is supposed to be done in a little bit more formal, so that students coming to participate in the summer programs in our region, they get to meet each other and they get together and they experience what the best that this region can offer us. So the Science Academy has given us this budget, and hopefully once the president of SPSTI is back, we will have a common subcommittee which will organize these things. So hopefully in subsequent years, we'll have a better way of doing these things. As at present, every lecture that we host, it is archived, so which prima facie it can be accessed. So right now they can be accessed only from the SPSTI site, but hopefully a new website for the Chandigarh chapter of NASI is coming up. There must be a website of INIAS already, CRICSI. So we will try to have these lectures linked to these lectures be posted on each of the sites so that the students can access, the other people can also access these lectures whenever they feel like at their convenience. So this information will also be hopefully in the next 1 month be sent to all what all lectures we have available with us in the recorded version. The idea of doing this year's lectures in a hybrid mode and also with the help of our own faculties in the CRICSI region was that these speakers are then available to us. So if we hold a lecture, like we are holding Dr. Nishima's lecture today, it's in the physics department. But once the lecture has been given by one amongst us, then any college in the city, any affiliated college of the university can approach the speaker, and you could invite the speaker to come and deliver the lecture in your own place. So, and since now we have the grant available from NASI, we will be able to support your travel also to go from wherever you are located to another institution. So this is a new dimension which has got added, so that once someone has prepared a lecture, now the lecture is in place, it has been delivered once, you know how to deliver it better in the next time. So this can have a multiplier effect, and we have a resource which Academy has made us available for 1 year. So hopefully if we do a good utilization and file the utilization in time, this grant 5 lakh rupees will continue every year. And to this can be added more support, like we now have a North Indian cluster, which has a larger budget, which will also have an office and people. So prima facie, the state has provided us support that we can enhance our activities. So I'm very happy that the physics department agreed to host this third lecture. We have a 4th physics lecture still left, which will be delivered by Professor Krishnamurthy, who is to come from Hyderabad. Then the economics lecture is to be given by Professor Upinder Sani. That will be in the 3rd week of January. Then there is a Nobel Peace Prize lecture to be given by Professor Ashutosh Sharma of the Department of Political Science. So this is how the series will go, and hopefully we'll try to finish these 6 lectures by the end of January, so that by the time we still have to do last year's lectures on Nobel Prize and the Turing Award, because otherwise the next year's awards will get announced in March, and if we don't cover up the previous ones, then there will be a backlog. So we will try to cover all this backlog before the end of February, so that we start with a clean slate when the March arrives. So thank you very much, and welcome once again.
Good morning, everyone. I'm happy to introduce our guest of honor today, who is Professor Navdeep Goyal from this very own Department of Physics. He did his MSc from the Department of Physics, Punjab University in 1986 and his PhD from the department in 1992. He has had postdoctoral experience as postdoctoral fellow from TIFR Mumbai, as well as from University of New South Wales, Australia. He joined the Department of Physics, Punjab University as a lecturer in the year 1995. And from 2010 onwards, at present, he is a professor here in the Department of Physics. His main area of research is experimental condensed matter physics, solar energy systems research, and power electronics. He has more than 34 years of research experience in these fields. He has great experience of leading international research collaborations in high-cost research projects very efficiently. He has around 141 international scientific publications to his credit, with more than 12,060 citations. He holds an H index of 18 and I-10 index of 44. Along with teaching and research activities, he has carried out administrative responsibilities over the last many years. A few of these are, he was the Dean Student Welfare from 2013 to 2016. He was Department of Physics Chairperson from 2017 to 2020. And along with these, he has been a member of Punjab University Senate and syndicate bodies, as well as a member of Board of Finance, Punjab University for several years. At present, he is the Dean, Faculty of Sciences, Punjab University. So, sir, now if you could please come and say a few words.
I'm thankful to SPSTI for inviting me to this lecture. In fact, Professor Grover was talking about the grant received from NASI. The way SPSTI is working, I believe if it can be registered as NGO, and there are some acts of income tax whereby it can become eligible to get grant, CSR grant. And there are, because CSR grant is given for promotion of science and technology. So probably there are so many industries in the region where one can get actually much better grant for these activities. So we should work on these things as well. See, when we talk about today's lecture on particular Nobel Prize on quantum dots, it's a field which is quite common when we talk about material science. In fact, material science, when one talks about whether one is a physics graduate or chemistry graduate, it really does not matter. In fact, when I did my PhD, my supervisor was actually a chemistry graduate, Professor K.K. Srivastava. And although he was a teacher, an excellent teacher in physics, I have not seen a teacher better than I have not seen a teacher better than him in this department, as far as physics teaching is concerned. See, quantum dots have many applications, all of us know. And the people are working on the technology of quantum dots for quite a few years now. In fact, for few applications, the technology has matured to a level where it is being commercialized, particularly the displays, because of the photoluminescence property can be enhanced a lot using quantum dots. So obviously the displays are being manufactured using quantum dots, and obviously because one is using this kind of technology, so number of pixels can be increased a lot. That helps in improving the resolution. But there are other fields also where when we talk about the quantum dots and use of quantum dots in technology, it can improve many things. If we talk about, for example, photovoltaics, people have shown that efficiency of photovoltaic devices can increase to a greater extent. Similarly, in fact, I see one more area, particularly where probably it is going to be commercialized very soon. That is when we try to use it as catalysis, because nowadays what is actually happening is most of the people, if we look at in the world, scientists or engineers, they are working in the field of energy. They are trying to see that one is able to produce energy or store energy, and that too in a green way. And there are reports now where it can be used as a catalysis for production of hydrogen directly from the sunlight. So, and that is something which is going to have amazing effects as far as technology is concerned, because right now what has happened is when we talk about the pollution, most of the pollution that we see in cities is coming from the vehicular traffic. Obviously, so what people started thinking was that about 10-15 years ago, that they can go back to electric vehicles, because when we talk about vehicles actually started with electrical vehicles, but because of the range problem and other things, they shifted to ICE engines. But then because of the improvement in battery technology, people started thinking about electrical vehicle first, because that, as far as technology is concerned, that was not an issue. There were further improvements because of the brushless DC fans and things like that. So they were able to adapt to electrical vehicles. But then when we are talking about electrical vehicles, ultimately the number of batteries, the storage that you require in a system, things are not that difficult. So people started thinking about hydrogen. Hydrogen, initially, what they thought is that it is expensive to produce hydrogen as compared to electrical vehicles. So if we look at the way manufacturers have gone about it, a lot of manufacturers initially, they have gone for electric vehicles, and many of them, in fact, dropped the idea of producing hydrogen-based vehicles, and Tesla was one. But recently, Tesla is also shifting to hydrogen vehicles now. They are also developing hydrogen vehicles. And reason is that now the technology is being developed in a manner that production of hydrogen is not going to cost much. That is the reason. See, if we talk about battery storage, the most efficient battery storage, if you talk about the storage cost, that is more than 10 rupees per kilowatt hour. So obviously, if because if one is talking about hydrogen, so 10 kilowatt hour plus the electricity cost that we can take into account. So roughly the cost comes to 16 rupees per unit, and that still saves you in terms of the fuel price. On the other hand, if we can produce hydrogen for less than that, which probably with the new ways of producing hydrogen, one can really, and that too, the green ways of producing hydrogen, one can really think about hydrogen as an economically viable solution. And that is probably the technology is again going to change in the coming 10 to 15 years. And it will be primarily because of I believe, the research that is going on with the help of quantum dots. So with this, I hope that we are going to learn a lot from today's lecture, because quantum dots is a field which is, again, Government of India is giving a lot of grant as quantum mission, and that is going to be worth it. Thank you very much.
So before we invite Dr. Nishima to deliver her lecture, it's appropriate to introduce her formally. So Dr. Nishima Wangu pursued her PhD degree in the area of nanobiotechnology from CSIR IMTech and moved further in the area of stem cell engineering and nanotechnology. At present, she's working as an assistant professor at the Department of Applied Sciences at University Institute of Engineering Technology, UIT, Punjab University. She joined PU as a DST Inspire faculty at its Center for Nanoscience and Nanotechnology in 2012 and got selected as a regular faculty member at her present position in UIT in 2015. Dr. Nishima has set up an independent research group which is pursuing work on the synthesis and applications of nanoconjugates. The thrust areas of the group involve the studies on the interactions between nanomaterials and biomolecules to develop multifunctional conjugates for sensing, drug delivery, and antimicrobial applications. She has around 70 research papers in high-impact international journals in the areas of bioscience, biosensing, nanoscience and nanotechnology, and material science. She has also applied for 2 patents. Her research work has been highlighted on the cover pages of reputed journals. She has had active scientific exchanges with international institutes such as Northwestern University, USA, Nanyang Technological University, Singapore, Osaka University, Japan, and ETZI, Germany. She is a recipient of UC Pant Memorial Award in the year 2013 in chemistry from Indian Chemical Society for her contribution in chemical sciences. She has been selected for DST Peirce Grant Award in the university based on her research profile. In 2019, she bagged the Best Researcher Award at the university. Besides that, she has also availed various research projects for carrying out the lab work from different funding agencies. She has successfully completed 10 research projects and is currently working on 3 more. Her PhD scholars include 4 PhD scholars who are undergoing research supervision at present, and along with 8 more who have defended their PhD already. Dr. Nishima is an active member of the North Central Zone of Indian National Young Academy of Sciences, INYAS, and recently she started the Women in Science WISE program at the university, where eminent women from around the globe are invited to share their life experiences. She was selected as the top 50 women in STEM in India in 2022 by the Principal Scientific Advisor to Government of India and Red Dot Foundation. She was also listed in Women in STEM Vanguards of India at 75 by the Confederation of Indian Industries. So I think we are all going to benefit a lot from today's lecture. So please, Dr. Nishima, you can just...
Thank you so much, ma'am, for your nice words and introduction. And at the outset, I would like to first thank SPSTI for giving me this opportunity to present this talk on the Nobel Prize in Chemistry of 2022. So I will first share my screen. So I'm going to talk about, as you know, the Nobel Prize in Chemistry, which is regarding the discovery and the synthesis of quantum dots. So what you see on your screen right now is one of these Nobel laureates, Monji Pavendi, and he's holding these beautiful quantum dots. And he's actually adding color to nanotechnology. That is why if you check the Nobel Prize in Chemistry webpage of Nobel Committee, you will actually see this paint brush. So this is a bucket having a paintbrush of a single material, which is giving you these different beautiful colors. So what I'm going to present today is about the Nobel Prize in Chemistry awarded to 3 people, and how they discovered these quantum dots, how they improved the synthesis of these dots, and what are the applications of these dots, and how in our region, particularly in my own lab, I'll share my own journey of development of these quantum dots. So these are the scientists, these 3 scientists, Monji Pavendi from the left, then Louis Bruce and Alexei Yekimov. These are the 3 people who won the Nobel Prize in Chemistry. The first, the second and the third one, Bruce and Yekimov, are actually the ones who discovered these dots, while Monji Pavendi is the one who revolutionized the synthesis of these quantum dots, because Pavendi was the one who actually developed a protocol for the synthesis of monodisperse quantum dots so that they could be further used for various applications. So in a way, I also agreed to Professor Nadeep Goyal and to Professor Gaurav Verma. They rightly pointed out that this prize is not actually about the Nobel Prize in Chemistry. Rather, I would like to call it a Nobel Prize in Science, because this is not only about chemistry, this is also about physics. So in fact, most of the people, even Pavendi and Yekimov, they were actually physicists turned into chemists. So I will share some stories about these scientists as well, and the other scientists also who were actually working with them, who did not win the Nobel Prize, but they actually had a lot of contribution to this Nobel Prize. So, before going into the present situation, let's go into the history of these dots, because these dots are not very new. So in 1937, it was Froelich who predicted that nanoparticles would not behave like other particles. So here I'm not going to describe nanoparticles because I'm sure all of us know what are nanoparticles. So it actually started with the synthesis or the development of glass. So the glass makers should actually be awarded with some kind of prize, because the glass makers were not knowing that they were making colored glasses, and what they were using were actually not anything else but nanoparticles, and particularly quantum dots. So what Yakimov also did was he started using that knowledge which was given by the glass makers to the development of these quantum dots. And at that time, he was working in the then Soviet Union, and he discovered these dots embedded in the glass matrix. But since he published it in Russia, so people outside Russia could actually not read his paper and get to know what he has done. So independently, Bruss also was independently working on this field. He also discovered quantum dots. So this is why Bruss and Yakimov both have been awarded with the discovery of the quantum dots. And what about Bhavanti? So Bhavanti was actually a postdoctoral student under Bruss. So he joined as a postdoc under Bruss and Bell Laboratories, and he was working on, when Bruss was working on quantum dots, so Bhavanti also started working in the area of quantum dots. So they were trying to synthesize these quantum dots in a very robust manner, and in a way that they could produce mono-dispersed material from quantum dots, but they were actually not very successful because it is not a very easy synthesis. So finally, in 1993, when Bhavanti joined as a young assistant professor at MIT, he was actually successful in the development of these dots along with his students. And let us meet these unsung scientists also, which are behind this quantum dots discovery and synthesis. So from the left, you can see Murray, Christopher Murray, then Manoj Nirmal, and Alexander Efros. So these were also one of those researchers who actually helped in the development of quantum dots. That is why the committee says that Nobel Prize winners almost never work in isolation, rather in collaboration. And all these people who were actually working in this field were a mix of physicists and chemists. So now let us come to what are these quantum dots? What matters? What is so special about these dots that they got the Nobel Prize? So just imagine, if you want to imagine the size of these quantum dots for those who are not from this field, just imagine a football. So a quantum dot is a crystal which is just like its size, just like the football is to the earth. So you can imagine how small is this quantum dot. And what sets it apart from other materials is the word called quantum confinement. So that is why we say the physicists are very important in this field, because they actually prove that quantum confinement leads to these exceptional properties of these dots and what sets them apart from the bulk materials. So what is this quantum confinement? Quantum confinement occurs when the motion of the excitons, the electron mode pairs, has been constrained to a confined space. This gives rise to different properties of these quantum dots. Now, how quantum confinement is achieved? For that, the Bohr's condition should be satisfied, and for that, the size of the nanoparticle, the radius, should be smaller than the exciton Bohr radius. So that what it leads to? It leads to quantized energy levels. So the energy levels are not continuous, but they are discrete energy levels. So you have discrete absorptions, and therefore you get size dependent emissions. So, and this size dependent emission is dependent upon their energy gap, as you can see in this diagram. So as you decrease the size of these quantum dots, this energy gap or the band gap, it increases, and therefore the emission also varies. And so this is not possible with a bulk material. So if you have a bulk material, by changing the size of the material, you cannot actually change the emission. But in case of the quantum dots, just by changing the size, so if you decrease the size, the lower emission you will get. So quantum dots defined as colloidal particles made up of semiconducting materials with diameters ranging from 2 to 10 nanometers. And more often or not, they are used as core shell quantum dots. So you have the core, which is responsible for the emission, and then on the core you have the shell. The shell has a greater band gap, and it improves the photophysical properties of these quantum dots. So the most important advantage of the quantum dots is that you have a broad absorption and a sharp emission. In contrast to the organic dyes, so what advantage this has is that you have a whole option of choosing the absorption, but the emission will always be narrow. So you can have multiple quantum dots of different sizes. You get the same energy of excitation and you get different emissions. So this is what sets it apart from the organic dyes in comparison to the organic dyes which have been conventionally used, FITC and rhodamine, which have been conventionally used for the internalization into cells like bacterial cells. So this you can see the quantum dots. A is under white light, which means normal light, and B, you see how they fluoresce beautifully under the UV light. So as I already explained, so we have a lot of advantages of semiconducting quantum dots over organic dyes. And also photoblinking is very less in case of quantum dots as compared to the organic dyes. So this also leads to improved photostability. That is why there is a whole spectrum of applications of quantum dots as compared to the organic fluorescent dyes. And we have also, in fact, in our lab, we are no longer using organic dyes, rather we are using quantum dots. Now let us go to some stories. Stories of the synthesis of these cadmium selenide quantum dots, the non-aqueous cadmium selenide quantum dots, especially which were made by Bavendi. So what Bavendi did was, he said that it is a synthesis born of necessity which unlocks a nano world of wonders. So while he was trying various methods of the synthesis of these quantum dots, he actually used this setup. So this is the setup. This is a 3-neck flask, and he used precursors. I will just explain to you which precursors he used. And then he used high boiling organic solvents under inert nitrogen atmosphere to obtain these particles. So this paper he published in JACS in 1993, along with his students Murray and Norris, who had a great contribution into this work. If you listen to the lectures of Bavendi, they are available on YouTube, you will get to know how important the contribution of these PhD students was for the Bavendi's group. So he synthesized this cadmium selenide, cadmium telluride, and cadmium sulfide quantum dots. In fact, when I started my PhD, so my supervisor gave me this keyword of working with quantum dots. So he was at that time, when I was in InTech, he was having a project with EPFL Switzerland where they had to develop a sensing assay based on quantum dots. So I started studying about quantum dots and I tried various methods, but they were quite unsuccessful. So then I referred to actually this paper. At that time, in 2004-5, I never knew that this is the paper which is actually going to fetch Bavendi the Nobel Prize in 2023. So I think it was some intuition that I followed this paper. And so I tried to synthesize these dots, the cadmium selenide dots, and it was not possible to synthesize it in InTech. So I used the chemistry lab of my supervisor at Punjab University. So what we did was we tried a synthesis of these using trioctyl phosphine and trioctyl phosphine oxide. So these are high boiling solvents. So this is exactly what Wendy also did, but instead of using dimethyl cadmium, which is very toxic, so my supervisor said that you should use rather cadmium chloride or bromide or acetate, which are relatively less toxic, and selenium powder. So in this lab at chemistry department, in Professor Vasim's lab, so they were synthesizing diselenides, ditellurides. So the synthetic method was actually different from this one. So in this method, we actually needed a very, very high temperature in the range of about 300 degrees Celsius. So we tried using normal oil, which we were using paraffin oil, we used sandbar, we used various things, but we were not achieving anything. So finally, we tried using silicon oil. So finally, with silicon oil, we did this. So we had this precursor of cadmium chloride. We added triethyl phosphine oxide, selenium powder, and finally, we tried the synthesis. Okay, so now you must be thinking why I am showing this cold drink bottle over here, this PET bottle of Fanta. So I will come to this story also, why I am showing this. Disclaimer is that I am not advertising this brand of cold drink. So I have nothing in relation to this. So why I am showing this is because when, so my supervisor at Intech, Professor Suri, he was very interested in that we should synthesize very high quality and very fluorescent. So he had put this pressure on me that you have to synthesize fluorescent quantum dots because we have to use them in an immunoassay, so they should be fluorescent. So after many trials and errors, so finally one day I started in the morning, and in the evening at around 6 o'clock, finally we had these quantum dots ready. So they were bright orange in color. So I immediately called him up and said that, sir, and I was very excited about the success of this incident. And I called him and said that, sir, I have been able to synthesize these quantum dots. And believe me, he was more excited than me and more happy than me. And he said that, okay, what is the color of these quantum dots? And I was not able to explain how fluorescent they are because I was a fresh PhD student. So I said, sir, it is bright orange, just like Fanta. So and whenever now I see Fanta, I remember my cadmium selenide quantum dots, which were bright orange fluorescent in nature. So this is how I also developed this methodology of synthesis. And if you see this slide, this is the original, what you call transparency slide of Bawandi. So Moishi Bawandi, when he was trying to do this synthesis, exactly the same synthesis, if you carefully see this encircled word, he has written magic. Instead of the reaction mechanism, he has written magic because it was working as a magic for him. At that time, he did not know what is the mechanism behind this reaction. So he labeled it as magic. So something magical was going on. And inference observations are so important in research because when he saw that he was using actually tributyl phosphine, and he was not getting reproducible synthesis and very neat synthesis. So what he observed later was that an empty older bottle of tributyl phosphine was actually giving better results than the new one. And then he did the NMR, and he later found out that it was actually the oxides which were giving better results than actually the phosphine. So what he termed at that time was that the results were episodic. So sometimes he was getting good results, sometimes he was not getting good results because the times when he was using the older bottle, he was getting the better results. So now he finalized in 1993 when he came to MIT that finally the ligands that are highly useful for this kind of synthesis are tributyl phosphine and oxide. That means DOP and TOPO. So these are exactly the chemicals that I had used. And the critical thing was to limit the nucleation. Nucleation means the generation of these small nuclei of quantum dots over which the growth occurs and they finally form these bigger nanoparticles. So coming now, later jump to when I joined here in this very department at the Center for Nanoscience, when the Nanoscience department was here as an inspired faculty. So I got this DBT, Department of Biotechnology Research Project on quantum dot-based detection of foodborne toxins. Now I had to detect toxins in the case of food. So it was not possible for me to use organically soluble quantum dots. I had to use water soluble ones. So it was a big challenge for me because when I tried exchanging the capping layer, which was mercaptopropionic acid, and beyond the quantum dots, they always quenched the fluorescence. So I had to directly use a method which led to the synthesis of water soluble dots. So I had a JRF position in my project. I conducted an interview and appointed a JRF. So it was Anuradha who was selected, and she was at that time, she did her MSc biotechnology, not in chemistry. So I was very, very apprehensive of her, and I thought she won't be able to synthesize these dots because it was not an easy synthesis. And we did not have anything because I had just joined, and we did not even have the Schlenk line. So at that time, it was a transition phase also because I was moving from nanoscience to UIT as a permanent faculty member. So in that lab, we needed to have a Schlenk line for the synthesis. And as you know, in research projects, if you have a particular sanctioned equipment, then only you can purchase it. So I did not have any sanction for this. So this girl was so smart. She actually went on her scooty to the market, and then she found out some scrap person who had this iron and steel, and she actually got this Schlenk line made from that particular person on the roadside, and we started this synthesis. So this is a method that has been actually developed in our own lab at UIT, and where we synthesize water-soluble, highly fluorescent cadmium telluride quantum dots. And the critical thing was the preparation of the sodium hydrogen telluride precursor. So after, I think it took us almost 8-9 months or more than that for synthesis, and this is the most critical step, which is the synthesis of the precursor, which we realized. And every step has to be done in very carefully. And this is where Anuradha's training in biotechnology came handy because she had worked in the area of RNA. And those of you who know this RNA work must be knowing that it has to be done with utmost care. And she was a biochemist working in the field of chemistry. And later on in the coming, in the new years, when the new students came from chemistry, she was actually teaching this synthesis to the chemistry students. And this is how where I proved that science is only science. It is not chemistry or physics. The Nobel Prize in this year, that is why I say it is for science, this chemistry one, because it involves all the fields of science. So these are the actual pictures of the synthesis of these dots. So you can see this cadmium telluride capped with cadmium sulfide core shell quantum dot preparation, which we did in our lab at that time. And even now, when we have to use some kind of quantum dots for essays, even now we can use those quantum dots which have been frozen at that time in 2016 or 17. So these are so stable that you lyophilize them and then you redisperse them and they will be equally fluorescent. So this is what I was talking about. On the left side, you can see the lyophilized quantum dots in a powder form, and then you redisperse them, you get equal fluorescence. So this is the whole setup, and if you can see, so initially when you have this injection of the selenium inside this round bottom flask, so when the quantum dots start synthesizing, it depends upon the temperature and the time. So the first aliquot would be the green emission one would be the smallest quantum dots, and gradually in a fraction of minutes or seconds, you will get the growth of these quantum dots, and accordingly you can take out aliquots of larger sized quantum dots as well. So in the same synthesis, in the same reaction vessel, you can actually get different sizes of these quantum dots. So what is the mechanism? The mechanism, there are 3 stages basically. You first form the tellurium and the cadmium monomers. In the case of cadmium telluride quantum dots, and you have to have a fast nucleation and very slow growth. So this is the actual trick of forming very good cadmium telluride nanoparticles or quantum dots, that the nucleation should be fast and the ripening, which is called the osmolar ripening, should be very slow. That is how you will get a monodispersed and almost the same size. So this is what Bhavandi actually found out in 93 when he successfully synthesized these quantum dots. So these are the aliquots that we had taken, and on the left side you can see these are under the white light and under the visible light, and under the UV light you can see the whole spectrum of emission from these quantum dots. So these two images below are the corresponding absorption spectra and the emission spectra of these dots, these quantum dots. And accordingly, so these have the sizes of 2 to 2.5 nanometers. The middle ones are 3 to 4 nanometers. Then you have 5 nanometers quantum dots, and finally the largest ones, which are the red emitting, are the 6 nanometers quantum dots. And these are the characterizations. So you can do the atomic force microscopy or the transmission electron microscopy to find the size dispersion or the sizes of these nanoparticles. Now, what actually is interesting about these dots are, so these are not limited alone to the lab itself and to the scientists, but these have now traveled into the daily lives of all of us. In fact, most of us are actually using quantum dots at our homes. When you see televisions, especially if you're having the Samsung QLED television, you are actually using quantum dots at your places as well. And another I think the most important and the most relevant application of these quantum dots are that it can be used for bioimaging, especially in case of tumor cells. So second, as I already told you, if you have this QLED television of Samsung at your places, so it is the Q stands for the quantum dot. If you can see, they have written 100% color volume with the quantum dots. So you have a blue LED, and initially a blue LED, and then you have red and green quantum dots. And from that red and green quantum dots, it produces the whole array of colors, and which is much, much brighter than the conventional LEDs. And this is actually a follow-up of the 2014 Nobel Prize in Physics in the LED area. So this is how it is transforming. So again, we have various applications of quantum dots, especially in case of live cell imaging, in case of sensing, in case of single molecule tracking. And over the years, especially in our country also now, we have seen a lot of applications of quantum dots and sudden jump in the even in the publications in case of the biomedical applications of these quantum dots. Because initially cadmium precursors were used, which were very toxic. But then they were gradually with time, as people realized they have a lot of applications in the case of biomedical areas. Then this cadmium core metal was replaced, and then indium phosphide. In case of televisions also, you have these indium phosphide quantum dots instead of these cadmium core ones. So in order to produce bioconjugates, especially for biomedical applications, so you have on the quantum dots, you have this ability, you can tailor the surface of these quantum dots. So you can functionalize with different kinds of molecules so that finally they can be labeled with the biomolecules. For example, you can either have the direct attachment to the ligand, or if you have carboxylated quantum dots, like what we prepared was MPA. So MPA, the sulfur is towards the quantum, mercaptopropionic acid, and carboxylic acid is towards the outside, which can absorb. So negatively charged groups can be there, and electrostatic interactions can be there with the biomolecules, or simple physical adsorption can also be there. Third is you can have iodine-biodine kind of interactions where you have receptor ligands which are very specific to each other, so that the binding is very strong. Then you can have zero-length cross-linkers also. A lot of chemistry has been done on the conjugation of carboxylic enamines, where you have this carbonamide chemistry, or homofunctional, bifunctional, or heterobifunctional cross-linkers are there. Plethora of them are available for the cross-linking. Then click chemistry can also be used for the conjugation of these quantum dots with the biomolecules, and especially in case of antibodies. So in cancer, specific antibodies can be labeled onto the quantum dots. Even you can cleave these antibodies with specific reducing agents. Like for example, this sulfur group can be exposed, and this can be bound to the quantum dots. So a lot of them we have already done. And in case of in vivo and in vitro imaging, quantum dots have been used a lot. So what is again the advantage? Advantage is that you have same material, Like for example, you have cadmium selenide or telluride, same material, different sizes, give the same excitation, you will get different emissions. So, but in case you use organic dyes, so for every particular emission, you will have to use a separate organic dye, separate fluorescing agent, and you need to have a separate excitation energy also. So quantum dots, you have the same excitation, different emissions, you get the labeling at different positions depending upon which marker it is targeting and which ligand is there on the top of it. And here also you can see on these are mesenchymal stem cells, you see how beautifully the quantum dots have been internalized into these stem cells. We had also used these quantum dots for internalization purposes, especially into the bacterial cells, because then you don't need any separate tagging agent. So this was the SARB research project where we were labeling the quantum dots with a cell-penetrating peptide, and then with the cell-penetrating peptide conjugated with the quantum dot, we could easily see that go into the bacterial cells when the antibiotic was loaded, and it was actually able to kill this bacteria. And then these characterizations can also be done, AFM, TM, the regular characterizations for this kind of conjugates. And here also you can see the confocal microscopic images of these dots, especially in case of bacteria, gram-negative, gram-positive bacteria. In both these types of bacteria, quantum dots could be internalized. And then we also use these quantum dots for a brain tissue analysis, which is actually a very difficult kind of analysis. So this TRH-based drug, analog of TRH drug, was encapsulated in these PLGA nanoparticles with the chitosan loading, because chitosan is a mucoadhesive. So in order to escape the blood-brain barrier, it was given through the nasal route. So kind of a spray, intranasal spray was developed. And we used actually the synthesized cadmium telluride dots to visualize this. So here you can see the brain. So in the next slide, I will show you in greater detail. So this is the fluorescent microscopic images of these brain excised from the rat. So you can see these cadmium selenide quantum dots, which are fluorescent, and you can see that the device, the medication that we had devised, the PLGA nanoparticles, were actually able to translocate through the blood-brain barrier, because this was an anti-epileptic application. So it had to go to the brain cells. So we did not use any organic dye, rather quantum dots. And then these quantum dots we have also used for the detection of pesticides. So this was based on the Inspire faculty project that we had, where I had to detect the pesticides using nanomaterials. So initially we used gold nanoparticles, but with the case of metallic nanoparticles, you have to use colorimetric sensing, which has its own limitations. But in case of when we used quantum dots, so we had this bright fluorescence and it was very sensitive. So the detection was very sensitive. So we used the fluorescent quantum dots, specific aptamer for the particular kind of the pesticide. And when this aptamer was free from the polymer, the positively charged polymer, then we had, in case of when target is not there, so these quantum dots got quenched. When the target was there, the quantum dots got quenched. When the target was not there, the quantum dots were still fluorescent. So it was a yes-no type of an assay, and also we could do the qualitative measurements. So this was published in Chemical Engineering Journal. And for that DBT project that I was talking about, so we could easily detect toxins using quantum dots. And we use two types of quantum dots, green emitting ones also and the orange emitting ones also. And we use the FRET mechanism, which is the fluorescence resonance energy transfer, to quantify the amount of SEB, Staphylococcal enterotoxin B, in the case of samples. Then, as I already told you, that we are using this quantum dots not only in the biomedical applications, but in our homes as well with this QLED. And this thing I already shared with you, that in these screens, the blue light is generated using the diodes. And these diodes were given the Nobel Prize in 2014. And quantum dots change the color of some of this blue light and transform it into red or green. And this makes it possible for us to have the three primary colors RGB for the television screen. So Bhavanti actually in his banquet speech after he got the Nobel Prize for this discovery, for the synthesis of this quantum dots, Monji Bhavanti said that wondering about how the atomic world evolves into the macroscopic one inevitably leads us through a wonderful new world. And this wonderful new world is the nano world, which we now call the realm of nanoscience and nanotechnology. In fact, if you read that the description of that Nobel Prize in the Nobel committee page, you will actually see that they have given the description of a movie of Dorothy. It is a very old movie of kids of animation where she suddenly wakes up with her dog and finds out that she's in a completely different land with different colors. And they actually related it to the colors of quantum dots. So quantum dots, which we are being honored today, Bhavati said, were at the birth of this new realm, and they shine brightly on its future and yet unimagined possibilities it offers. Like Adil said very rightly, that we have just started the applications of quantum dots. We are yet to see the future, and there's a whole lot of future for these kind of quantum dots. We have just begun, especially in our country, we have just begun, and we have in the coming years, we will see a lot of applications. Like nobody imagined at the time of Ekimov that the quantum dots, which were being used in the glass matrix, which would actually come to solution phase by Brass, and then to the large scale synthesis by Bhavanti, and then we come to our homes through our television. So he said that, so tonight let us raise a toast to the human drive for exploration and to the future of nanoscience. So he knew that at that time also that there are certain things with the quantum dots which are still not known, the applications, and in the coming years, for sure, we will see these applications. So with these words, I would like to acknowledge, first of all, SPSTI for giving me this opportunity to share the work that was done behind this Nobel Prize in Chemistry of 2023, and to share our own story as well, and to know about the applications of these dots. I tried to remain as basic as possible, so please excuse me if I used terminologies which were not very familiar. I'm also very, very thankful to Department of Physics, Punjab University, who agreed to hold this lecture over here, and Department of Applied Sciences, various collaborators and family and well-wishers, and all the funding agencies which give all these grants for doing this work. So quantum dots are basically small size, big effects. So I always say that people or things which are small may not be very small because they have a lot of applications. So people who say that you are short height or something, I say don't go by the height or by the size, focus on the worth of that person. So quantum dots have proven that philosophy as well. And Richard Feynman in 1959, actually this is a famous quote from him, that there is plenty of room at the bottom. And over the years, this thing has been established that really there is plenty of room at the bottom, which is yet to be explored. So thank you so much for giving time, and I'd like to have any questions if you have. Thank you so much. Yes, Richard.
Thank you, Dr. Nishma, for such a wonderful talk. So I have also worked with quantum dots during my PhD work for conjugating the realignment. But as you told that the synthesis is at very high temperature.
Yes.
So at that time I tried with only commercial as well. So I just want to know, is there any method that is low temperature or a pre-chemistry type that can be used to try the quantum dots?
Yes, thank you, Richa. So the high temperature one method that I was telling you was the original method by Bhavanti, which used triactyl phosphine and oxides, right? That was at 300 degrees Celsius. But the one that we are using in our lab, which is for water-soluble quantum dots, which we use for, that is not at 300 degrees Celsius, because you don't use high boiling solvents. Because of the use of high boiling solvents, you needed to have high temperature. Now that you have sodium hydrogen telluride, you don't need to have, you should not have that temperature. So you can use those particles.
What is temperature?
That is much less than 300 degrees Celsius, much less than that. So because triacetyl phosphate is a solid at room temperature. So if you don't have 300 degrees Celsius, you won't be able to have that reaction. But since you're not using this anymore, you're having these water soluble quantum dots. So 100 degrees Celsius, you can actually synthesize that. Yes.
The gold nanoparticles, colors of gold nanoparticles, something known for very
Yes.
long.
Yes, sir.
The quantum dot field came into focus only when the semiconductor
Yes, sir.
came in.
Yes, sir.
Why this? What is it that the gold,
So gold nanoparticles.
why are the metallic nanoparticles not achieve all that in the semiconductor?
Yes, sir. So this is mainly because gold nanoparticles, of course, had its and still has its own applications, but towards a different end, because the major importance of metallic nanoparticles arises because of their surface plasmon resonance, the SPR effect, and only those so that has found applications in of course in optics, also in biomedical, also for photodynamic therapy. So gold nanoparticles have been used a lot. But the problem is that, as I said in my sensing methodologies as well, so in case of sensing and in case of other applications, colorimetric methods are not very good, because colorimetry, see, you have then cross absorbance with the other things also which are present. For example, if we are doing sensing, we have other ions also. So the gold nanoparticles, they quickly aggregate. Even if there is a pH variation, ionic changes, then it will aggregate. But in case of quantum dots, you have this strong fluorescence. And since it is passivated also by an additional shell, so the chances of aggregation are very less. And because you can have the same particle and you can tune the fluorescence, so that is the most important application of these quantum dots. That is why they are way ahead of the metallic nanoparticles.
Anyone else? We as you said, some of the these quantum dots.
Yes.
As you said, some of the quantum dots, they are made at very high temperatures. So does their property changes when we use them at lower temperatures? Or
No,
once they are formed at high temperature, then should we have to use them at such those temperatures for their
no. So
properties at lower temperatures?
okay, so I will again explain. The high temperature is required only for the mixing of this high boiling solvent, triethyl phosphine oxide, with the precursor molecules. So once that precursor is formed and the quantum dots are synthesized, then you have to remove that heating. You have to actually cool it down, because then otherwise the growth will continuously go on. The particles will start growing. So you have to reduce the temperature. So that it is used at room temperature just. It's only the synthesis, especially of those particles. So that process, organically soluble, is not used nowadays, because then you have to exchange the layer with some water soluble layer. So rather we are using the method that I showed you with the water soluble layers. Thank you. Yes.
So, I'm just a general question. What do you think will be future applications or future implications in the sense where this field is leading?
Yes. So this field is actually leading to a lot of applications that I just explained, but two areas, because that is the reason why I highlighted only those two areas. Those are the biomedical applications and the electronical. So biomedical applications, because especially in case of cancer, where you need to visualize the tumor, so you need to have near infrared emitting dots as well, because there is a lot of autofluorescence when it comes to live imaging. In case of in vivo imaging, there's a lot of autofluorescence also. And the dyes that are conventionally used, they are not very good, because they're not very photostable. So in that case, quantum dots. So if you notice that Nobel committee also wrote this point specifically, that it is going to be a very important tool for the surgeons. So this can actually save lives. So the surgeon can actually visualize, particularly see that particular tumor area. So that is going to be a very important application. And of course, in case of electronics, it is going to be a quantum dots, as we have already seen it in case of televisions.
One point I actually, like for example, nanoparticles or nanocrystals, they have shown ability to interact with other type of molecules and generate newer materials. Where do you think quantum dots will lie in that field? I mean, nanoclusters, when you interact with some organic molecule, we actually get that there are different materials are coming up. Where is quantum dot lying in the respect of nanoparticles and nanoclusters as a different entity and its interaction with the material?
See, I explained earlier also, in case of quantum dots, you have this ability of tailoring the final product. Why you have that? Because surface functionalization of this quantum dots is very easy as compared to the other nanoparticles. Why? Because as I was just explaining, the stability in case of these dots is higher as compared to the nanoparticles. So like we synthesize this mercaptopropionic acid, so you have carboxylic acid and you have a variety of linkers that you can conjugate with the other particles onto the surface of these quantum dots. Right? So you don't have to have an additional step for the surface functionalization as in the case of metallic ones and then labeling it with other biomolecules. And the fluorescence will also be synced.
Thank you very much.
Thank you. Thank you.
So formally, I'm presenting a vote of thanks as an acknowledgement to Dr. Nishima for presenting a very colorful lecture and bringing art into science also. So right from the word go when you started with Fanta, which actually matches my sweater right now, to the LEDs, which will be the future, probably flexible electronics also, and to the medicinal chemistry and diagnostics and therapeutics, where probably quantum dots will play a large role. So we all understand that science actually knows no boundaries, and we have to work in conjugation with each other as quantum dots are. So they're successful because they easily conjugate with the other elements, whether they're organic or inorganic. So thank you very much, Nishima, on behalf of SPSTI, CRIC, INEAS, and NASI. I thank you for presenting this wonderful lecture on the Nobel series. And thank you everyone for patient hearing and immense support. Thank you very much. I thank all the people who also joined online. So we end up the lecture here.
Let me announce that SPSTI has been organizing. SPST has been organizing lectures on the National Mathematics Day for as long as I can remember. I think probably right from SPST was created in 2009, and from 2010 they have organized this National Maths Day lecture every year. Of course, the National Maths Day was pronounced only in the year 2012, but Ramanujan's birthday, the Indian mathematicians have been commemorating for much longer. The Government of India accepted to designate December 22 as a National Mathematics Day only in the year 2012. So this year we are organizing 2 lectures on the National Maths Day. Fortunately, a very bright young mathematician who is very popular to give expository lecture in public. He is visiting Punjab University at the invitation of UIET, the institution to which Nishima belongs. So UIET is holding a workshop. They have invited Apurva Khare. So he is in town, so we have taken advantage to have a series of lectures from Apurva Khare. So Apurva Khare gives the Sarvdaman Chawla lecture, which is an annual lecture on behalf of Department of Mathematics of Punjab University. So Apurva Khare gives the Sarvadaman Chawla lecture on December 20th at 4 p.m. in the mathematics department. And this is the sixth Sarvadaman Chawla lecture on behalf of our university. And Sarvajan Chawla is perhaps the third most famous mathematician that India had in the 20th century. If it's Ramanujam one, Harishchandra second, then Sarvadaman Chawla is the third one. And Sarvadaman Chawla is credited to have established a school of mathematics at Lahore. So a book came out 2 years ago which talks of schools of number theory in India. So it's first, of course, talks of Chennai Madras School of Mathematics, okay, from Ramanujam came. The second school of mathematics is actually the Lahore School of Mathematics, set up by Sarvadaman Chawla, whose father was also a mathematician, Gopal Singh Chawla. And the third one is Harishchandra, who was a student of K.S. Krishnan at Allahabad. Then went on, Krishnan sent him to Baba, Baba sent him to Paul Dirac. So from physicist, he's transformed to a mathematician. And from Dirac, he went to US, and then he got a professorship at Institute of Advanced Study, Princeton, from where he never came back. But we are very lucky that our university has this great mathematical heritage. So he gives this Sarvadaman Chawla lecture on 20th of December. Then the ISR Mohali jumped in and they are having a National Maths Day lecture from him at 10 a.m. on 22nd of December. So the first lecture on 20th is going to be at a research level. The second lecture on 22nd of December at 10 a.m., which is going to be at what I call as a college and university level. And the third lecture is at a school level. And that is at the Amity University, Punjab, where Professor Kohli is the Vice Chancellor, who is the President of the Nasi Chandigarh chapter. So Apurva gives these three lectures. In fact, two lectures he gives back to back, one at 10 o'clock, the other at 11:30. And all the three lectures will be covered by SPSTI in the hybrid mode. So all the three lectures will be archived. So those of you who cannot join for the three lectures, you can listen to these lectures at leisure by accessing the SPSTI page. So thank you all for coming today, and please keep joining and spread the word around. There is an archive of all the lectures which have been posted since the year 2020. Pandemic was bad, but pandemic has given us this resource of a great archives of lectures. If you actually, a series of lectures that we held during the pandemic was institution building and the research initiatives in India. So what have the scientists contributed to independent India? It is the institution building and nurturing and providing opportunities and nurturing people at all levels to pursue not only science and technology, but everything at the frontiers of knowledge. So this is the contribution of the teacher scientist to independent India, and all this is beautifully documented in a series of 19 lectures which were hosted by SPSTA. Then we ran a series which is about the vision for the institutions in our region. So there is a series of 12 lectures. You also figures in one of them. Every famous institution, Chandigarh, what is the vision which the contemporary heads of those institutions have projected out to the public? And this is a vision. Long before Modi ji came with this Viksit Bharat at 2047, the Chandigarh institution had already projected their vision for 2047, because we said it will be India at 100. And this is a vision of our institutions for India at 100. So that is also beautifully documented. And the third series which we have commenced this year, it is inviting the decorated scientists from our region to come and share with the general public, okay, the good work that they are doing. So they are expected to describe in simple terms, which the public can understand, why the society values their contributions to the academics. So that series is also running parallel. And this series is an open-ended series. It will keep on running so long as people from our region are honored by the society at large. So I think it's a good movement. Let's continue it, and I'm very happy that INEAS joined it. INEAS initially was a Chandigarh region INEAS, but now INEAS has expanded to cover the whole of northern region. So we'll have more and more young people joining this caravan, and I hope finally it will have effect in the society for learning and pushing the frontiers of knowledge. Thank you very much.